Hello, my name is Moxey from Wolfspeed Power, and welcome again to In the Studio, where once more we are here to have a good old chat about silicon carbide. And to do that, I'm privileged once more actually to introduce a gentleman that really actually doesn't need an introduction outside of his 32 years of silicon carbide magnificence. He is the Gandalf of wide bandgap, Mr. John Palmour.
Thank you. I'm sorry I didn't wear my hat.
Next time. Okay. So last time we went through silicon carbide versus SiC versus GaN. Lots of questions we get asked all the time, and hopefully we discuss those in detail with education. Now I want to switch to another series of questions we get. What's next? You know, we're knocking it out of the park at 650 volt, 900 volt, 1200 volt, 1700 volt. No doubt about that. You know, it's being embraced, high volume, accepted. But people, particularly more at the academic, deep design level conferences, are keen to know what's next. And I'm not talking, way beyond the horizon.
Sure.
But within our lifespans of work. So I thought we would bring in mid-voltage.
Happy to do it.
And I know it's a particularly fond subject of yours.
It is.
When we say mid-voltage, let's start at the start. What are we talking?
The way I view it is typically kind of 3.3 kilovolts and up. And in the case of silicon carbide, up goes much further than in the case of silicon.
Right.
Silicon, in terms of IGBTs, goes up to about 6.5 kilovolts.
Okay.
Thyristors may be up to 10 kilovolts, but they have to be cooled very heavily.
This is like static VAR compensation and the big Einstein type
power
things.
Power management. But in the case of silicon carbide, we can do a unipolar device, a MOSFET, up to 10 kilovolts.
10 kilovolts?
Yeah, 10 kilovolts, okay. Whereas silicon typically stops around 650 volts.
Okay.
If you want to go to a bipolar architecture like an IGBT, we've demonstrated devices as high as 27 kilovolts. It's the highest solid state switch ever shown. So it's a whole different realm than silicon plays in today.
Different league, totally.
Completely different league.
So just for the completely uneducated like myself on this, so you're saying MOSFET to 10 kV and then silicon carbide IGBT beyond that. What's the breakpoints there?
Well, it depends on the application. I would say 10 kV is kind of a crossover point. Actually, the way to think about it is very much what you see in silicon. Yeah. At 650 volts, you really start talking about IGBTs for big power because the MOSFETs start getting very big and very resistive. And so really above 650 volts, it's really mostly IGBTs. In silicon carbide, it has 10 times higher breakdown electric field. So that crossover point is basically about 10 times higher. Okay. So 6.5 kilovolts, that would be a MOSFET. At 10 kilovolts, it can be a MOSFET if you want to operate at high frequencies, or an IGBT if you want to operate at lower frequencies and have lower conduction losses or more current. So 10 kV would be kind of a crossover point, and it really depends on the application you're trying to fill. And then above that, the MOSFETs start getting very resistive and too large. And we really see IGBTs above that. We've also worked on GTOs, gate turn-off thyristors.
Seriously? Wow.
Oh, yes.
It's a blast from the past, the GTO.
They're very, very good, very high conductivity material. We've done that for some research contract work as well.
So this really does cover the entire mid-voltage spectrum.
The entire mid-voltage spectrum and far more, because we can go to so much higher voltages that silicon just has not been able to address. Even the 6.5 kilovolt IGBTs are very rarely used because they're so lossy. They're barely usable.
That's true.
Really would only use them at kind of 60 kilohertz or something like that.
Yeah, because solid state power conversion up at that voltage is not that common. It's really still magnetics.
Yep.
Okay, so this really does truly enable a brand new space.
It really does, and we've talked a lot about 650 volt up to 1700 volt.
Yeah.
And the savings with silicon carbide are undeniable. It brings a lot of benefit, but as you go higher in voltage, that benefit gets even stronger. So whereas we might cut the losses at 1200 volts by say 70%, at 3.3 kilovolts, it's 1/10 the loss. It's like 90%. You go above that, it's starts being orders of magnitude. There really is no comparison between silicon and silicon carbide. Silicon carbide opens up an entirely new realm that you can operate in terms of high frequencies. And that allows you to look at things like solid state transformers.
Yeah, exactly.
As opposed to using a big, huge 60 kilohertz heavy, transformer that's lead and oil. We were able to use a very small, it's a misnomer, solid state transformers or transformerless systems is a bit of a misnomer because you still have to have a small high frequency transformer to isolate.
Yeah, it's for safety reasons.
But it's the size of a bread box as opposed to, the size of a car.
Well, you're absolutely right. I'm picturing, these oil-filled transformer substations that are the size of a small European country.
Exactly.
Compared to something that could be the size of a wheelie bag that you can pop on the overheads.
Exactly. And that opens up all sorts of different possibilities of what you can do.
So grid, solid state grids, because it makes sense. We spend our entire lives trying to make things more efficient.
Yep.
And if in the context of renewable energy, solar and wind and that type of energy storage. But then it's absolutely bonkers in my mind that energy then is taken and then transported hundreds of miles away to the point that it's used.
Yep.
And in that, it's lost half, roughly speaking, plus or minus, of what it is. So you're really saying that obviously this mid-voltage transformation also can be localized as well, right where you've got that point of renewable energy, the solar panels, the central inverters, the wind turbines, or whatever's, a bunch of mice generating a load of stuff. I don't know. Mm-hmm. Anything that's not coal powered or fossil fuel powered. And then you can solid state transform it in a tiny little area very efficiently as well, more efficient than magnetic wise.
Yep.
And then you go down the chain with silicon carbide to point of load or point of use where we make the energy conversion more efficient there too.
The grid, particularly in the United States, is very much built around the concept that there's one big, large power plant and it transmits out there. So you fill the bucket at the power plant, but while you're carrying it 100 miles away, quite a bit gets sloshed out of there.
Hub and spoke type thing.
Yeah. And, so a lot of the energy that's generated is actually lost in transmission. Now, obviously, the power company would prefer not to lose all that. But the other thing that's coming with the advent of all the renewables is you're going to have a much more distributed power grid where you've got a solar farm over here, you've got a windmill over here, you've got a power plant over here, and you've got energy storage over here. And they all are putting power onto the grid and potentially pulling it off in the case of energy storage. So you need a very high efficiency way to transfer that energy up and or pull it off. So that's what grid tied inverters are. Typically you can do a grid tied inverter with a solid state transformer. And we've done a number of system demos. We did one that was funded by Department of Energy to do a 250 kilowatt grid tied inverter. So it's trying to tie to 13.8 kilovolts on the grid side. And we
13.8 typical localized grid. Yeah.
And we did that with power modules using 10 kilovolt MOSFETs, 10 kilovolt silicon carbide MOSFETs.
Okay.
You have a solid state or a high frequency transformer, and on the low side we were feeding out to what would be a solar grid array at 500 volts DC. So
13.8 to 500.
To 500 volts.
And DC, the important bit is DC.
Yeah. So
DC coupled.
So we're doing both the solid state transformer and the AC to DC conversion. So that's been very successful. We did a solid state power substation for some work that was funded by the Navy that was a 1 megawatt demonstration, again, based on 10 kilovolt MOSFETs on the high side, 1200 volt MOSFETs on the low side. I think that was, again, 13.8 kV down to 1000 volts. These demonstrations have all been done. There's been a lot of university work around the world demonstrating solid state transformers, and it just works. It's far smaller, far more efficient, and quite reliable so far, at least for the early demos.
It's early days, and interesting you mentioned megawatts.
Yep.
It's kind of cool that we're getting up to this 10 kV and above. But it's only really recently, and especially with Wolfspeed, that we can inject some amps into that. Because
Yes.
10 kV at 1 amp, not particularly handy unless you're doing some sort of weird voltage multiplier thing to get your hair spiky. But 10 kV at 10,000 amps or 1,000 amps starts getting pretty tasty.
It really does, and typically as you're going up in those voltage ranges, you are going up in total power. So megawatts are the name of the game.
Yeah.
And but the beautiful thing is, if you can get that bus voltage up, it doesn't take that many amps, so you can get a lot done without too much real estate of silicon
If you keep
carbide.
the voltage high.
Yeah, there's a lot of attraction for grid-tied inverters for solar, as I said, wind, and then I mentioned energy storage. So that's particularly interesting because you have to pull the energy off the grid, down convert it to DC to charge up the batteries. Yeah. And then when you want it, you've got to pull that back out. So it's got to be bidirectional, and you lose energy both directions. And so efficiency counts double. It's round trip energy efficiency, and silicon carbide can actually make that, let's say, 7 to 10% more efficient in round trip efficiency.
7 to 10%. So I can't remember the amount of terawatts of energy storage predicted, but 7 to 10% of many, many, many terawatts is going to be
It's a
huge.
big number, and it's 10% less battery you have to put in that storage, or 10% more energy you can store. And all of that is very important, because if you can store the energy, then you can have more overall alternative energy.
Yes.
Because the sun doesn't shine all the time, the wind doesn't blow all the time. You've got to store that energy, and that means there has to be a steady floor of basically hydrocarbon, fueled baseline energy. If you can, the more energy you can store, the more you can bring that baseline down of the polluting energy.
Yes.
And add more capacity for renewable energy.
Yeah, I mean, if you can generate and store properly, you get rid of the need for that burst mode of fossil fuel reliance.
Exactly. And you don't have to do much reading of the news to know how what a hot topic that is, hot literally, these days, to try to move to a greener climate to avoid climate change. So there's a big push for that.
Yeah, and you and I have spoken about this before. We saw some really progressive stuff, exactly what you're saying, over in the UK about electric charging, huge electric charging infrastructure at 5, 6, 7 megawatts of charging stations with renewable energy on site, energy storage on site, bidirectionally tied to the grid.
Yep.
And right now, they're doing a fantastic job, but it's all been slightly lower voltage because there's not the technology available today to take it to that right voltage levels. But I'm thinking not too distant future, silicon carbide will be able to enable that.
Yeah, the fast charger example is a very interesting one, because if you own a gas station or it's soon to be charging station, you have to put that big, huge transformer we discussed on your property, and it takes up a huge amount of area. But you have to do that to feed all that power to those fast chargers. And with high voltage or medium voltage silicon carbide, you could conceivably do grid-tied fast chargers. Each one could actually be tied with a very, quite small box directly to the grid. So with silicon carbide, you could conceivably do grid-tied fast chargers. Each one could be grid-tied with a relatively small solid-state transformer. So the operator of the station doesn't have to devote so much space, which is expensive, to these big, huge transformers and power distribution to the charger.
It's a real example in front of people today.
Yeah. So there's, and silicon carbide is in fast chargers, but only on the low voltage section. The high voltage is typically going to be done with a transformer.
Yeah, it's the section where you plug into your car at 400 volts or 800 volts, depends on what battery you've got. So upstream of that is where the the future action's going to be.
Exactly. So it saves that costly space and does it extremely efficiently.
Including enabling the energy storage as that buffer.
That can be a bidirectional charger. So there's a lot of interest in the cars being temporary storage devices, right? You've got a tremendous amount of energy storage on each vehicle. So not only can you charge, but if you're at work and the grid needs it, it can also pull it off.
You can give back.
You can give it back.
Yeah. So. Which people think about that as on a residential level. If you've got any little excess charge in your car in your garage and the power goes out, fine. But you're absolutely right. On a grid utility level, if you're lucky enough to generate megawatts of solar during the great day and it's being stored, the amount of cars at night time being charged, one or two here or there, give it back.
Yep. Economically swap power with the power company, I guess.
So also with energy storage, we have grid resilience.
Yes.
The grid is in essence, an infinite source, but it's so fragmented and spread out that it suffers.
It suffers quite a bit, and we've seen examples of how unresilient the grid in the United States can be with some famous blackouts up in the Northeast. An ice storm brings everything down in Texas.
Yes.
So there's a lot that can be done to make that more resilient, and I'll talk about some of that later also.
Yeah, so if you had your own energy grid level connectivity and energy storage locally, you could avoid those blackouts.
Exactly.
Okay, so you just teased a little bit more there. So we're talking about grid solid state activity, but what else does mid-voltage silicon carbide kind of get us into?
Well, I think the first place you'll see it, and in fact it exists to a certain extent even now, is train drives, electric train.
Okay.
So what is that? It's a motor drive. It's just a big high-powered motor drive. Pulling power off the grid, off the high voltage line,
yes.
Again, maybe 3.8 kV. You bring it down to the train, you have a big heavy transformer on that train, and then you have the motor drive, which is typically going to be a multi-level IGBT design.
It has to be today.
Well, it has to be today. But again, you could do that with the highest voltage IGBTs, but they're so lossy that typically they don't. They'll do a 2 or 3 or 4 level design because they want the speed of the lower voltage IGBTs, 1200 volt or 1700 volt IGBTs, because they're not as lossy as the high voltage.
Just stack them up.
And then you multi-level topology to be able to handle that thing. So, but those multi-level topologies take a lot of parts, and they're quite complicated to design.
Yeah,
and
control strategies.
Control strategies. Yeah. So, but that's what is done today. So let's imagine instead that you have silicon carbide, 3.3 kV modules or 6.5 kV modules. You could pull that down with a solid state transformer. You can push that big heavy transformer off the train.
Yep.
Saves a lot of space, a lot of weight, and then you can do the motor drive much more efficiently. And now instead of a 4-level design, maybe you do a 2-level.
Simplicity,
more
efficient,
simpler design, fewer parts, etc., and far more efficient. So even at 3.3, we talked about, it's an order of magnitude improvement in switching losses. And it's just, there is no comparison to what silicon carbide can do at those frequencies.
Yeah, you've got to do
high frequencies.
You've got to do what you've got to do today.
Yep.
You've got to work with the best stuff you have. But, trains, locomotions is a brilliant example because it depends on what train, it's different voltages, but it's all minimum 1700 volts, tends to be a lot higher with the big intercities and the larger product. You've said it. If you've got something that moves and there's a limited space and you can get rid of a massive copper transformer, that is just huge in itself. Then if you're more efficient, then I suppose if we are living in fantasy land, we can regen back in when it breaks. As well, or if you have your own energy storage on board, it can store that. And I do know that silicon carbide is already in locomotives and trains for the auxiliary power.
Yep.
Not the motor drive, but the auxiliary power. So it's proven its reliability, its consistency.
And it is being demonstrated in the motor drive in some trains in Japan. Some of the metro lines in Japan are actually running with silicon carbide in the train now, and it's proving to provide a really big benefit. The efficiencies, most train drives are pretty efficient, but if we can just save 2 or 3% efficiency, remember these trains run 18 to 24 hours a day, every day for 20 years. So you add up that lifetime savings in electricity, it's a staggering number. So we can make that not only more, efficient, but lighter, smaller, et cetera. I had one guy say, well, we can't push the transformer off the train because we need the weight for traction.
Oh, but otherwise it's just going to wheel spin.
Yeah. But I'm sure there's much cheaper ways to weigh down a train, put a slab of lead in there.
It seems a bit Jurassic to keep a transformer just for those reasons. But, and America's developing with huge emphasis on infrastructure, more trains, but obviously Europe, India, Asia, massive cultures for rail transportation.
That's where the big market is Europe and Asia for electric train drives, but there will be more and more here in the United States as well.
This is change at a gigawatt level again, just like we spoke about before.
Yeah.
So what else? We're on through trains.
So traction control in general is what that's called, but kind of an offshoot of that and is just medium voltage motor drives. So much like a train, this is really huge, heavy industrial equipment. This could be mining, drilling, crushing, all sorts of this really heavy stuff.
Yeah.
And depending on what you're trying to do, if it's mining, it probably has to be portable also. You've got to be able to put this on a truck.
Degree of portability, yes, absolutely.
And take it to wherever you're mining or wherever you're drilling. One of the attractions is deep water drilling. So you can't drop the entire motor drive 2 miles down in a salt water, right? So that has to be up on an oil derrick, and it takes a tremendous amount of space and energy. So we can make it more efficient, but the big attraction there is to shrink the overall size of these really huge industrial drives, particularly in things like an oil derrick or a remote space where you have to haul in your power and your drilling equipment.
Yeah,
that's a huge win. Just moving these things around is a tremendous amount of logistical.
I hadn't honestly thought about that, because that's all for the general consumer, the general Joe public. That's all behind the fence.
It's all behind the fence. You don't know it happens, but these are absolutely huge drives. Huge. It could be compressors for really compressing down gases, et cetera. But this is big, huge factory. We can offer again a huge impact, because the medium voltage devices in silicon today are just so lossy.
And an application that is very visible to the general public, wind.
Right now, all of the power electronics are up in the nacelle, the thing at the top, and then they have to bring that power down and push it out. One of the things that I think would be very attractive, because there's a huge copper cable that comes down that long tower. Copper is very heavy and expensive. So what if you could just double the voltage that you generate the power at up in that nacelle? You cut the copper cost in half, or triple it. Those things are all possible with silicon carbide, where they would not be possible today. So save a lot of copper, save a lot of weight, and get higher efficiency. Particularly if you're out in the ocean, you've got to, typically they do like an HVDC transmission.
That's true. That's true. And please talk to me about HVDC. Little segue in there.
High voltage DC power transmission is what's typically used for distributing power under, for long expanses. Let's say it's underwater, across a bay or a large expanse of water. So you got to drop a cable, and the most efficient way to cover a long distance like that is high voltage DC transmission. So what they do today is actually use IGBTs, or formerly thyristors, and they have to stack it up. So think if you want to do 100 kilovolts, and that's really just the very bare minimum for a high voltage, because 200, 300 kilovolts up into megavolts. what they do is they stack these devices all in series. So let's say each device is allowed to block 4 kilovolts.
Yeah.
Well, just to do 100 kilovolts, that's 25 devices in series. The voltage drop for each device might be 4 volts. So the VF of all these 25 devices in series is enormous.
Yeah.
It's whatever that is, 70 volts or something like that. That is, the amperage you're conducting times 75 volts. That's what has to be dissipated.
Yeah.
So these are typically buildings that are at least 2 stories high as these things are stacked up with a tremendous amount of water cooling. Typically it would be, you'd either see a big heavy cooling tower outside or quite often a lake or a pond, where they just keep recirculating.
So many watts need to be extracted.
Exactly. So now let's imagine you used 10 kV devices in silicon carbide, and you could double that voltage. The way to think of it is you could cut in half the number of devices in series.
More than
You're
half.
going to cut the VF in half.
Yeah.
That means that's half as much energy you're dumping out into your lake.
Simpler designs.
And it's that much more energy the power company gets to deliver to the end application. So HVDC is a very interesting application. It takes a long time to get there, but it will have tremendous advantages in terms of efficiency. Just
generally, operating in DC is great for silicon carbide. Yes, you have to have some sort of transformer somewhere for isolation, one-to-one transformer where you've got to obviously convert. But when we can manipulate and switch mode DC to DC and exploit switching frequency, reduce the size of all those magnetics, caps, cooling, whether it's a 2 kilowatt server power supply or a 20 megawatt solid state grid tied system, the principles are pretty much the same.
They are, and this is what silicon carbide is meant to do. And medium voltage is where it shines actually the best because it's just unheard of capability.
So why aren't we there? When do we get there, Dan?
Because the biggest part of the market is in this lower voltage market. We have a huge opportunity in front of us with the BEVs and a number of industrial applications. But we are absolutely still working on the medium voltage applications. I think 3.3 kV will be first, and we have a number of people interested in those for drives, traction control, et cetera. But we are very dedicated to continuing to go up that voltage, 6.5, 10 kV, and then potentially even IGBTs in the future because of the unprecedented capabilities that we can offer. 10 kilovolt MOSFETs can operate at 20 kilohertz.
20 kilohertz, whereas a multi-level IGBT system would be hundreds of hertz, I'm guessing?
Something like that, yeah. It's really unprecedented capability. You can take you can do a solid state power substation that would, in silicon, be the size of a city bus and make a silicon carbide version that's the size of a Miata. So
what's holding it back?
It's really just there's 2 things. One is we have a huge market in front of us now that we have to pay attention to.
EVs and charging and solar, etc.
But we're absolutely working towards that. We feel very confident in the reliability of all these things. We've done a lot of work in power module design. As I said before, when we were talking about lower power, you have to really optimize the module design to take full advantage of the silicon carbide. We've had a lot of good progress there. So it just, we're getting close. But as you go up in voltage, I will say it's uncharted territory in the power module design area because you need packaging is a challenge.
Yes.
So if you're going to do a 10 kV power module, you got to have isolation voltage of 15 kV. Can't have any partial discharge. And when you get up into voltages that high, there's all sorts of
there's some weird stuff.
Weird stuff wants to happen. So the packaging gets more difficult without a doubt. Mm-hmm. And it just hasn't had to be done before. Then you talk about, 15 or 20 kilovolts, it's totally uncharted territory. So there would be a lot of work to be done, not just on the device side, but in the packaging side.
Yeah, because hockey pucks are still de facto for thyristors and GTOs.
Yep. they're still out there.
And they've been around for 40 odd years. So advancements, it's only as good as the slowest advancement.
Yep.
And the packaging needs a lot of stuff. What about reliability? If you're going to put something on a wind turbine in the ocean, it's got to be reliable. It can't just be fixed on a whim.
Has to be extremely reliable,
Yeah.
because think about the cost of having to fly out into the ocean, land someone and some heavy equipment on the top of a nacelle of a wind turbine. It's extraordinarily expensive. So they would very much not like to do that. We haven't released a product yet, but we actually have demonstrated a lot of reliability testing on all those voltages, 3.3, 6.5, 10 kV. And the good news is the electric field in these devices is basically the same, it's actually a little bit lower than the electric field for those lower voltage devices. So the fundamental reliability physics is all pretty identical.
Scalable from what we know.
Very scalable.
Scalable from our 7 trillion field hours.
Yep. The only thing is they have to be bigger chips because of the higher voltage, they're more resistive. But, we feel very, very good about that.
And of course, packaging, as you said.
Packaging has to follow.
Well.
There's new regulations around packaging, the modules for traction control for train drives, roll to rail. So we're developing all our modules to try, to meet those roll to rail specifications.
Yeah, just thinking humidity. It plays havoc with my hair, let alone a semiconductor device. So,
well, I don't have that problem, Guy. but yes, humidity is definitely an issue that you have to account for, because these are all going to be systems that are sitting outside, exposed
20 miles
to some degree to the elements.
Offshore or even trains or whatever. So
yeah.
A lot of good stuff to come for sure, and it feels like it's not just Never Neverland stuff. This is.
It's not.
I'm almost touching it.
Yeah, this will add on incrementally, as we go up in voltage, but eventually also, I mentioned grid management. So there's a lot of things you can do. Part of the issues around having these blackouts that we do periodically in this country is the grid is mostly managed by switchgear still.
Yes, that's true.
And
very
it's
true.
very slow and slow to react. So if you start doing grid management with solid state, you can now react like that. If you see the power sag, boom, you can reroute energy, you can do all these things.
Yeah.
But that really requires very good, very fast and efficient medium voltage devices. And silicon carbide can fit that bill. So we can do grid management, we can do stat vars and all these other grid management things with grid tied energy storage, et cetera, to much more efficiently handle the grid and let it react much quicker.
So you're doing solid state switchgear, which implies then that the mid-voltage solid state circuit breaking and protection can also replace mechanical super slow relays.
Exactly. And there is a lot of interest in solid state relays, for instance. Great application for GTO, for instance.
Yeah. Seriously, as the saying goes, the future is that bright, you're going to have to wear shades on this one.
Absolutely.
And
I don't see silicon, while silicon never sleeps at lower voltages, this is a really tough one for silicon.
It is, and silicon's had a good swing at this, and if it's not there yet, I don't think it's going to be.
I agree.
So looking forward to this, and thank you for sharing, a little taster and whet the appetite of what could be coming in the near-term future. And hopefully you'll join us again in the studio. Some of this information, a little bit futuristic, is on our Knowledge Center and website for reference. But please join us again next time. Thank you, John.
Thank you, Guy.